Okay, let's have a look at the production of fertilizer from raw materials. This ties in with the chemical equilibrium processes and also with the fertilizer industry. This diagram that is in your science clinic is really important, and it shows you all the pathways for the processes. So for instance, here are your two raw materials that go into the Haber process, and then these go into the Ostwald process, which produces ammonium nitrate and potassium nitrate. But then the Haber process is also used to make ammonium sulfate fertilizer in the contact process. And so the Haber process is the root of all of this, because you can see most of these have got ammonia in them. Look here, ammonia, and then the ammonia goes into the Ostwald process. And then here to make ammonium sulfate fertilizer, here's the ammonia again, and here's the phosphate fertilizer with the ammonia. So you can see here there's ammonia in basically everything. So the Haber process is the root of all of this. But you need to know the Haber process, the Ostwald process, and the contact process, okay? And you need to know the steps of them and what their catalysts are. So if you look down here at these superphosphates and the triple superphosphates, and it just gets the formula, the chemical formulas for the compounds. Look at this one over here. They're kind of mind-boggling. I've never seen them really ask about this. They're quite interested in the contact process and this formation of oleum, and obviously we see the Haber process quite a lot. But you will need to know the Haber process goes with ammonia, the Ostwald process goes with nitric acid, and the contact process goes with sulfuric acid. Okay, so let's go have a look at all of these things and how they happen in industry and why they're important. So if you have a look here, this is what a fertilizer plant would look like. Okay, this is in 2018, end of 2018. Omnia, who's a big chemical company, started making a fertilizer plant, 695 million rand to start making this, and this is just the nitrophosphate plant. Okay, so you can imagine this is big business. In South Africa, Sasol, which stands for the South African Synthetic Oil Limited, is a major fertilizer producer, and like this is a fertilizer plant. This is what it looks like, because it's actually not just one system. It's because, like I showed you in this previous slide, you can see here, this ammonia that you produce in the Haber process goes into the Ostwald process, but it also gets mixed with the contact process to make ammonium sulfate. Now this ammonia is a gas, and it's a horrible gas. You aren't going to want to ship this gas all over the country everywhere. So what you're going to do is you're going to try and put all of the plants together and ship all of the stable raw ingredients together. So you then basically build this massive structure that makes all the different kinds of fertilizer in one place, all based on the Haber process. So let's have a look. Ammonia, here is the ammonia molecule. We use ammonia for nitrogenous fertilizers, so to give nitrogen to the plants. So anything that's got ammonia in it can give nitrogen to the plants. And so it's used to produce urea, which is a kind of fertilizer, ammonium nitrate, and other things. And it's prepared by the Haber process. Okay, this is some kind of an amide here. This might actually even be urea, and this is like ammonium nitrate. So let's have a look at the Haber process first. This is nitrogen plus hydrogen goes to ammonia. It's a chemical equilibrium reversible reaction, and the forward reaction is exothermic. So when you make this, you use a catalyst of iron or iron oxide mixed. Okay, you have to have a high concentration of reactants to favor the ammonia yield. So at a low temperature, you get a high yield because it's an exothermic forward reaction. So what they do is they increase the temperature and they get a low yield, but they get it pretty fast. So this is a very slow reaction. Like if I mixed nitrogen and hydrogen in the classroom, you'd probably find that the hydrogen would react with something else before the nitrogen, because you just wouldn't end up with ammonia. So to make it financially viable, the temperature at which it's financially viable is 400 to 450 degrees Celsius, sorry. I always forget you people don't know centigrade. And you have to do it at a fairly high pressure, because you will get a high yield. Okay, so high pressure not only favors the reaction rate, it also favors the forward reaction of this equilibrium reaction, because 4 moles play 2 moles. Okay, so increasing the pressure favors the forward reaction, and it also favors the reaction rate. So at about 200 atmospheres of pressure, you get an acceptable yield and an acceptable rate and an acceptable cost. So these are the optimal conditions to carry out the Haber process. So you need to know the catalyst and the temperature and pressure conditions. So how do we actually get the raw materials to make the Haber process? Here's a diagram showing you ammonia gas and hydrogen gas mixing, okay, and then being pressurized, going over the catalyst, and then going into a cooling chamber, and at the bottom of the cooling chamber you get out the liquid ammonia, and then it recycles the nitrogen and hydrogen. So remember that if you want to drive the equilibrium of a reversible reaction forward, you need to continually remove the product. So when they continually remove the ammonia, you're still left, because it's an equilibrium mix with nitrogen and hydrogen. So at the other end of the chamber, they will take the nitrogen and hydrogen back out and put them back in as what we call feedstock. So you'll have the raw nitrogen and hydrogen from the way you make the nitrogen and hydrogen being mixed with some unreacted mix that's gone through this whole process. So it cycles, okay? So the nitrogen comes from the fractional distillation of liquefied air. So air boils at minus 196. Remember, the air is boiling all around you because it's in the gas phase, so it must have already boiled, okay? It boils at minus 196, and we then get the nitrogen has got a different boiling point to the rest of the things in the air, so you can get it out the top of the distillation column. So if you watched my other video, you'll have seen this animation before, that you just pump in air from the atmosphere in here, and then you squash it, you compress it, and then by the gas laws the air heats up, and then once you've got that squashed and heated gas, remember, if you squash it you might turn it into a liquid, and they squash this heated gas and they pass it through something to cool it down, okay? So first they squash it, which causes heating, and then they have to cool it down, okay? So then once they've cooled it down, the particles will get closer together, and then as they release the pressure, they let it go into another chamber and they release the pressure, and it instantly turns into a liquid. So this is a phase equilibrium thing. I'm going to show you a picture on the next slide of how phase equilibrium works. But basically they're just fiddling with compression and heating and cooling with the melting and boiling point of this liquid, because pressure changes melting and boiling points. So then once the air, this is now liquid air, seems strange, but liquid air comes out of here, it's at minus 200 degrees, it gets pushed into this container, and the nitrogen goes out the top and the oxygen goes out the bottom. The oxygen goes out as liquid, but the nitrogen is boiling at minus 190 and goes out the top, and that's how you get the nitrogen out, and the oxygen's like a byproduct. If you have a look at this thing, it's called a phase diagram, and if you go further in chemistry you'll learn about these. This is a pressure temperature thing, and so you know we always give boiling points at sea level, which is 1 atmosphere pressure. You can put nitrogen, and if you put nitrogen at different temperatures and pressures, you can get it to have different melting and boiling points. So for instance, at 10 atmospheres of pressure, can you see that this is the solid liquid boundary, so this is the melting point. So at 10 atmospheres of pressure, the melting point has changed considerably, and at 100 atmospheres of pressure, look here, the temperature has gone up again. So this is why they fiddle in the previous slide with the temperature and pressure conditions. So let's go back to this now. We've figured out how we got the nitrogen from the fractional distillation of the air. Now we need to get the hydrogen into the system, okay? So in South Africa, it's different in different countries in the world, but in South Africa, the Sasol is actually vaguely famous for this. They get the hydrogen from coal and steam. They call it syngas, or you can get it in other places from steam catalysis of natural gas, which is methane. We don't actually have a lot of methane here. So here's the carbon solid mixing with water. This is very, very high temperature gaseous water, and you get carbon monoxide and hydrogen and some ash out of this. Okay, so this is called syngas, and they burn coal in a kiln. A kiln's a giant, really, really hot oven, and they make sinter. So you burn coal in a kiln to make sinter, and then this sinter, this special sinter, is this carbon over here, is used to make the synthesis gas. So the sinter plus the steam goes to carbon monoxide and hydrogen. Okay, and then some of the carbon might also mix with oxygen to form carbon monoxide. So they do this in special conditions so that you don't end up with carbon dioxide or combustion or whatever. And this process has some byproducts like phenols, which are organic ring molecules, naphthalene, this is mothballs, sulfur, tar, pitch, oil, nitrogen compounds, xylene, organic chemistry, and ammonia. So there's obviously rubbish in the coal. The coal is not pure carbon, and from that, this is where these byproducts come from. But this is how in South Africa we get this hydrogen here, which we need for the Haber process. So what happens here now? We figured out how we got the nitrogen. We figured out how we've got the hydrogen. We pump them into a container. We pressurize them to 200 atmospheres. And then the pressurized two gas mixes are poured over the catalyst to speed up the reaction in the reactor. And inside here, the reversible reaction occurs. And so some ammonia is going to be formed. And then they pump this mix. It's an equilibrium mix, so it's got nitrogen, hydrogen, and ammonia. They pump it out here and they put it in this cooling chamber. And what happens is, if you know your intermolecular forces, you'll know that ammonia has hydrogen bonds. Okay, so the hydrogen bonds are stronger than the London forces, which the nitrogen and hydrogen have. So remember, there's nitrogen, hydrogen, and ammonia in here. And then the nitrogen and the hydrogen only have London forces, so they've got a high boiling point. So they go zooting out back into the reaction mixture. And meanwhile, the ammonia, which has got hydrogen bonds, is strongly attracted to each other, and it liquefies and can be taken out the bottom there. And that's how we end up with liquid ammonia from the Haber process. Okay, and I'm going to stop here because I'm sure your ears are tired.